Hello everyone, my name is Massimo Stella and my talk is going to be about phonological networks. More in detail, we are going to discuss the role of phonological networks in investigating the structure and the constraints of the human language by also using a set of suitable reference null models. The main object of investigation is the so-called human mental lexicon, an analyzed dictionary that psycholinguists suggest might be encoded in our mind and which stores words and concepts according to their linguistic data. For instance, as reported in this naive picture, the mental lexicon might contain a visual representation of a word or the phonological instructions on how to pronounce one. At the phonological level, the mental lexicon can be modeled in terms of a phonological network, as Vitevich suggested in his work from 2008. In a phonological network, nodes represent phonological transcriptions of words, and two words are connected together if they are phonologically similar, which is, if they differ by the addition, substitution, or deletion of one phoneme, like cat and can, for instance, in this picture. By using data from Wolfram research, we built a phonological network larger than Vitevich's one, starting from a dataset of roughly 29,000 English words. The resulting network was highly disconnected, with a giant component of roughly 10,000 nodes, as reported in this plot. Also, the English phonological network exhibited a heavy tail in the degree distribution and a strongly pronounced core-periphery structure. Last but not least, it exhibited high assortative mixing by degree. In order to better understand these features, we asked ourselves a very important research question. Contrary to previous preliminary studies, in fact, we realized that the phonological network is actually embedded into a very peculiar discrete space. An example is reported in here for a simple binary alphabet. In blue, we consider all the strings of a given length we can obtain by combining zeros and ones. By connecting these pseudo-words according to phonological similarities, we obtain a collection of regular interconnected graphs that we call layers. Now, if we identify in red only those words actually appearing in a given language, we can realize that the phonological network made of such words is actually a subgraph of a much larger and more regular structure. As it happens for almost every embedded network, the English phonological network might inherit some topological features from its underlying space. We have therefore to distinguish between them and other features that might actually reflect the constraints present in the organization of the mental lexicon. In order to make this distinction, we need null models. The simplest null models that we came up with are percolation-like experiments. We consider each word as a sequence of phonemes, and by assuming different constraints from the empirical data, namely the word length distribution, the phoneme frequencies, and the phoneme correlations, we literally assemble artificial sequences of phonemes, thus creating artificial pseudolexica. From them, we build the relative artificial phonological networks as reference models. From this table in here, we see that even by inserting all the three constraints at the same time, these percolation models cannot retrieve the same size and the same connectivity properties of the empirical phonological network. This is what motivated us to come up with the second generation of null models, in which we have a network growth over time. So at each time step, we generate an artificial word, as we did before, but now we insert it in the network and we can reject it with a given probability f if it will not connect anywhere. This process mimics word derivation, a process of language development, since it will mainly accept new words that are similar to the ones already present in the network. Optionally, we can further reject a given word with another probability PR if its connections would increase its degree above a certain upper threshold. Now, the results of this model are quite interesting. When we try to identify which acceptance probability 1 minus f matches the size of the empirical giant component of the empirical network, we see that the more constraints we insert, from type 0 to type 2 experiments, the higher the acceptance probability can be, which is quite natural to expect. Also, the order in which we insert words matters. Inserting words at random, as in the black curves, always results in a smaller acceptance probability compared to the cases when shorter words are inserted first in the network, as in the red curves. Differently put, our growth models quantitatively show that there is a higher likelihood for the mental lexicon to be assembled over time by starting from shorter words first. This result agrees with a common conjecture in psycholinguistics, but there is more. If we plot the degree distribution in our percolation and growing network model that is reported in here, we see that we always have a heavy tail behavior. This is an indication that such feature is a consequence of the embedding space of the phonological network. It is not necessary to invoke any preferential attachment procedure in order to reproduce it, contrary to previous claims. Furthermore, if we look at the empirical data, we see that there is a cutoff for higher degrees in here. Which we are able to reproduce only if we insert the optional rejection of words more connected than a certain threshold. This finding indicates the presence of an actual constraint on word organization, so that there cannot be more than a certain number of phonologically similar words on average, otherwise they could be confused with each other. At a closer look, unfortunately, even the growth model failed at reproducing the connectivity of the empirical network. In fact, we saw that all our models lacked many connections, preferentially among shorter words, which are situated within the core in the empirical phonological network. This is what motivated us to come up with a second generation of null models where we now bias the network growth. We force shorter, highly connected words to be inserted in the growing network core, while longer words tend to stick within the network periphery. These core-periphery models do match many lower-order statistics of the empirical network. This is what motivated us to use them for having a look at higher-order network statistics, such as the local clustering coefficient. Our null models are still more cliquish than the real network, which also displays a peculiar behavior of constant average local clustering coefficient, the black dots in here, over node degree. This marked distinction between our null model and the real data might be the indication that there is another constraint in the mental lexicon about triadic closure. This might also be the case, since we know that higher clustered words tend also to be more confused, so that they tend to be minimized. To conclude, the take-home message from this brief talk is that phonological networks are really interesting tools for investigating the human mental lexicon once they are considered as spatially embedded networks. In fact, some of their features might be inherited by their underlying space, like it happens for the heavy-tail degree distribution. In fact, they highlight the presence of several constraints present in the real language about word confusability and about the likelier assembly, over time, of the mental lexicon by starting from shorter words first. So, let me thank you with phonologically similar words. Thank you for the present of your presence. For further details, I am ready for questions. And also these are the two papers that we published these years as reference. Also, I would like to acknowledge my supervisor, Marcus Breda, and the whole DTC in Complex System Simulation at the University of Southampton. Thank you. I'm ready for questions.